So as Lori mentioned, I'm going to be talking about chi-square today. So I actually have a decent amount of experience using chi-square. My whole dissertation, the primary analysis was chi-square. A couple of manuscripts I published before that was chi-square. When I took initial stats, I didn't really learn it. It kind of was brushed over. But as I got into these analyses with these manuscripts in my dissertation, I had to learn, I guess, the hard way and kind of on the fly. And I had a lot of meetings with my stats professor just because there's a lot of things I didn't quite understand. But hopefully I can present it in a way that makes sense to y'all. So we will be covering chi-square, but there's also other analyses that we will be covering because there's more than just the chi-square test to run when you run a chi-square. There's some other variations you can do based on your data, based on some of the assumptions you meet and stuff like that. And we'll go over all of those today. So here are our aims. So like I said, we're doing chi-square. We're going to look at contingency tables, what exactly those are. We're going to look at likelihood ratio, which is an alternate to chi-square, as well as McNair's test and Fisher's exact test. We'll be looking at those as well. The odds ratio, which for those of you who don't know, odds ratio is a way to determine effect size of a chi-square test. And we'll go over that. And then we'll do log linear, which may be a little bit out of the scope of chi-square, but this is using 3 or more categorical variables, and that is a little bit more complicated. So we'll go over that briefly just so y'all can see in case you have analysis like this you're going to have to do in the future. So what exactly is a chi-square test? What it is you're basically determine association between 2 or more categorical variables. And when I say categorical variables, you can also think nominal variables, same thing. But it's basically meaning the number associated with that data point doesn't necessarily have a actual number, meaning it's more of a placeholder for something else. So for example, if you're measuring if individuals were smoking or non-smoking, you might mark that with a 0 for no or a 1 for yes. You might want to see if males are more likely to be non-smokers than females, and you can run a chi-square. You can also run it with some ordinal data if you want. You can also run some survey data, but just know you have to have limited categories. I've seen it run with 5 responses to a survey, but no more than 5. I've only done it with 3 responses from a survey. So it gets a little bit more complicated than that. So if you have more than that, I wouldn't run necessarily a chi-square, but there is an option to do that with ordinal data as well. One thing to remember about chi-square is we're not necessarily examining the differences between variables. We're looking at association, and that's something that reading through papers, reading some of the things online, some people get this confused. Association is not a difference, and we'll see what that exactly means in a little bit. We can find differences between groups, but just know when you find that chi-square statistic, it's not necessarily telling you that the 2 groups are different. It's telling you there is association between your one categorical variable and your other categorical variable. Last thing, most often is use a 2x2 contingency table, which looks like this. Basically, you have your variable X up here, your variable Y. You have responses, yes or no, for each of them. And then your column totals, which is the combination of this column, your row totals, and then your total. These will look like a lot more sense when I get into the SPSS, because this is what you probably see during your outputs, and it helps interpret what your data is actually looking like. You can do a larger than a 2x2, but there's certain tests you might run differently if you do more than a 2x2, as well as the interpretation gets a little bit complicated with a 2x2, but it is possible. For my dissertation, we had a 2x4. So I had an intervention and a control group, and then I had 4 outcome variables that they could be categorized in. Yeah. So some examples you could run. You could do the number of people voting for different politicians. Again, you can mark that they voted with them with 1 for a yes or 0 for no. Number of students pass, fail, number of patients waiting list controls who are free from diagnosis, or a number of clients who choose a different category of satisfaction scale, either being satisfied, neutral, or not satisfied. These are just some examples, but there's really unlimited examples you can use as long as your data is categorical at the end of the day. So for all your math heads, this is the actual chi-square equation. I'm sure you'll never see this or have to actually use this. But when I was in school, we had to do hand calculations for a couple weeks before we were able to actually do the SPSS. But what the chi-square statistic is doing is, again, not measuring differences. It's measuring if the frequencies that you're observed for a certain variable is the same as the frequencies you might expect to get by chance. And you'll often see, and you'll hear me say today, observed versus expected frequencies. And that's what the chi-square model really is determining. Are your observed frequencies different from the expected frequencies if the null hypothesis was true, meaning there was no differences between the groups? And that expected frequency you'll see often with every test that we'll run, and that's basically what the model is running at each time, is your observed versus your expected. And you'll see a little bit more broken down in a little bit. This is a little bit more information on those expected frequencies I was mentioning. Again, what you're doing is taking the expected number you would expect to get if you had the null hypothesis being true. If we see that there is a significant chi-square result, what that is telling us again is that there's a significant association between the categorical variables in the population, not necessarily saying that there are differences. Yes, you can conclude that there are differences most likely, but just know when you're reporting, you're more reporting that there's an association rather than a difference. But I'll explain how you can see those differences in a minute. So some alternate tests you can run to chi-square. When you go into SPSS, and I'll show you that as well, what you can select is chi-square. You can also select likelihood ratio, Fisher's exact, depending on what you're looking at. What the likelihood ratio does that's different from chi-square. Chi-square, it takes your actual data points, what you actually found. Where likelihood ratio is creating a model based on what you found, and then taking that model and again, comparing it to the expected model. It then creates a new statistic, and that statistic is looking at the observed model that the chi-square test made versus the expected model that the chi-square test made, and seeing if those are statistically associated. This is most often used when you violate assumptions of a more than 2x2 table. If we'll go over the assumptions in a second, if you do not violate the assumptions, go ahead and just run the chi-square as normal. But if you do violate, run the likelihood ratio instead, as well as if you have a pretty small sample size. Sample size is a big deal with chi-square. One of the assumptions, which we'll see in a second, is you can't have any values less than 5 or any cells within the contingency table less than 5. It seems like on the forehand, it might not be that hard to violate the assumption, but when you start having a 2x4, 2x6, whatever the contingency table may look like, it's very likely you will violate that assumption. So I'll provide some ways to account for that. But one of those ways is using the likelihood ratio statistic. Fisher's exact test is the non-parametric version of chi-square. This is again when you violate assumptions, but it's only used in a 2x2 table. It's not recommended to use it in anything larger than that. And to do Fisher's exact, it's the same process, except you're going to select exact in the options menu, which we'll see in a minute here. McNemar's test is another option for chi-square, but this is used with paired samples. And this is, again, strictly used for a 2x2 table. And each of those variables have to be dichotomous. So it's either a yes or no, or 1 or a 2. It can't be anything larger than that. Again, it's recommended that you don't run anything other than McNair's if it's larger than 2x2. The final option, which we're not going over today, just because I felt like it's a little out of the scope and a little bit more complicated than anything we're doing today, is Cochran's Q test. This is when we're running repeated measures with more than 2 time points. So you could do that at 2x3 table if you wanted to. I won't get that in today, but all the other ones we'll talk about throughout the presentation today. So for our assumptions, the first 3 are ones you'll usually see in most statistical tests, other than obviously nominal, because we're working with nominal data. But the first assumption is all variables are nominal. The second one is each has mutually exclusive categories that include observations. The third is measures each variable are independent of one another. And again, all 3 of these, if you've entered your data correctly, you cleaned it correctly, you should already have these accounted for before you start your analysis. The final one, though, is you should have sufficiently large expected frequencies, meaning there's no more than 20% or no more than 20% that are less than 5. This is, again, an issue when you have larger contingency tables. I've dealt with this issue when I was running my dissertation data. And what we did is we dichotomized the, well, we not going to dichotomize, we combined one of the variables. So instead of being a 2x4 table, we made a 2x3, and that helped account for those violations and assumptions. If you do violate this assumption and you can't reduce your sample, you can't reduce one of the variables, you can still report, but just know that you're losing a lot of power with this violation. So make sure to report that in your writing when you do have this violation of this assumption. I faced this violation in my dissertation data in a couple of the tests because we just couldn't reduce it. And I made sure to add a statement saying that we violate this assumption, the power is lacking, and these results should be interpreted cautiously just because there's nothing we can do about it. You should have no values less than 1. Yeah, again, it's on the surface, it looks like you probably won't have that problem, but once you see the contingency tables, it's very likely you might have that issue and have to account for it. So basic steps, this is just scientific model, how to start from finish for your chi-square tests. You state your hypotheses, you set your significance, which is typically 0.05 in most chi-square tests. You create the contingency table. That's something that SPSS can do for you. You don't necessarily have to do that yourself. And it'll do all the percentages that you're looking for, not necessarily any hand calculations you'll have to do. You can put your chi-square, you determine your degrees of freedom, you make your decision based on what test you're going to use, your likelihood ratio, your Fisher's exact, etc. And then you summarize results. For the chi-square result, it's pretty easy interpretation. When we get to log linear, it becomes a little bit more complicated, and you'll see how that unfolds in a second here. So interpreting chi-square. So when you find your chi-square test certificate, again, that is giving you your overall result. Is there an association between the two variables? Now, just because there's a significant chi-square result doesn't necessarily tell us where these differences or these associations are coming from. And we can do that using standardized residuals. These are more beneficial when you do a larger than 2x2, so 2x3, 2x4. When you do a 2x2, you can assume which variables are contributing more than the other ones. However, when you have 3, it's almost impossible to figure that out. That's why you just do the standardized residual and you can find it. Again, for me, this part took a while to grasp when I was reporting my results, just because I couldn't understand that chi-square wasn't necessarily telling us the difference. It was telling us the association. So I had multiple edits back from my stats professors saying that I was interpreting it wrong because I kept on going back to the differences and kind of ignoring the standardized residuals. But those are very important for you to report. With the standardized residuals, what they are is basically a z-score that's determined by chi-square. And how we determine significance is if that score is higher or lower than 1.96. If it's higher, then it's significant. Even if it's on the negative side, so negative 1.6, if it's -2, that's still a significant at 0.05. Other ones we'll see in a second as far as 0.01 and 0.1. But those are your gauge to see, okay, I know that this variable specifically is contributing most of this results, and I can say that they might be more or less likely to have the result that we're looking for. Finally, you can determine effect size of chi-square using the odds ratio. Unfortunately, SPSS does not determine odds ratios for you, or not that I've figured out how to do at least. So that's something you still will have to do a hand calculation, and we'll go over that in a second here. So as I mentioned before, what the standardized residual is actually telling you is the difference between the observed count and the expected count, and then the standard deviation of that expected count in the chi-square test. And it's really a measure of strength of difference between the observed and the expected. So this is where, again, we really get that differences between group statistic that we're looking for. It gives you basically the significance of your cells to the chi-square value. So you can pinpoint saying this specific data point is contributing the most of this significant association we found in our chi-square. Again, going back to the values, if you're in the negative, what that's telling you, if it's higher than -1.6, that the observed frequencies is significantly less than what is the expected frequencies of the model. On the other end, if it's positive 1.96, that's telling you that you have significantly greater than expected observed values in the model as well. These are very simple to determine. It's just a simple click on SPSS, and I'll show you all that soon. So here's odds ratio. Again, this is the hand calculation you're going to have to do. For me, I often refer back to this picture just because looking at a contingency table on SPSS and figuring out exactly which is A, which is C, B, and D, etc., can be a little confusing. I want to note here that with odds ratio, you're only really allowed to do an odds ratio for a 2x2. You can still do it by 2x4, 2x3, or whatever it may be, but just know you only compare two variables at one time. So you can compare case A to case B and then case A to case C to see the differences between the two. You can't necessarily find an odds ratio for A, B, and C. Not that I've experienced, at least anyway. So what you do to define your odds ratio is you're taking the history of exposure. So again, if they have something or not, you can mark a 1 or 0, and then no history. And then you're going to compare your groups. So here is the actual equation you're looking for. You have A over C divided by B over D. I know that looks confusing, it doesn't make sense now, but once we get some numbers in there, it'll make a little bit more sense to see what we're doing. And this, I threw that in there for some reason. My wife and I are on a huge Hunger Games binge the last couple of days, so I felt it was appropriate for this presentation. So a quick example, this comes from Andy Field's book of statistics. I'm sure most of y'all have experienced it. If you've ever read it, it's very, I don't think inappropriate is the best word, but he tries to make light of statistics and not necessarily just train you with terms and boring language. He tries to make it a little bit more interesting. So he has some examples that are a little bit far-fetched and a little bit out there, but it keeps your attention a little bit when you're reading through the book. I found it free online, so if you haven't read it before, I suggest you do. There's a lot of good stuff in there. There's a lot of good examples you can use. He gives example data. So for this example, he asked the question, can animals be trained to line dance with different rewards? He had 200 cats in total, and he had two different training methods he was going to implement, one being using food as a reward and the other one being affection as a reward. He then wanted to see if they would dance based on the reward they got. So they marked it either they danced or they did not dance. And what he wanted to determine is the number of animals that could dance or not with each reward condition. So what you're going to do first is create your contingency table. Again, this is something that SPSS can do. You don't have to necessarily do it yourself, but this is what it looks like. So out of our 200, we can see that we had 28 that danced when they had food as a reward and 10 did not. And we had 48 that danced when they had affection as a reward, 114 that did not. So just as an eyes glance, and I always do this in my contingency tables just to see if I can make logical sense of the data. But what we can see here is most likely food has a positive effect on them dancing because we see there's more that dance with food as a reward than no, where affection probably doesn't have that big of an impact because we saw more that did not dance than did dance when they had affection as a reward. But again, that's not statistically accurate right now. That's just something in my observations that I can assume based on the data. And again, this helps kind of wrap your mind around what you're looking at before you actually get to the results and all the numbers and whatnot. So it's always good to just look at the contingency table first and get an understanding of what the data might be showing once we get to our statistics. So I added this for SPSS just so you all could see. I'm sure, I know some of you don't use SPSS, but it's just a good basis to start with. So what you're going to do is go into descriptives and go to crosstabs. There is no chi-square necessarily test. It's always through the crosstabs menu. First, you're going to add your rows and your columns. Your rows, the type of training. So again, did they have food or do they have affection? And then the columns is did they dance, yes or no? When we go to exact, this is where we can select Fisher's exact test. By default, it's used the Monte Carlo, which I've always used in the past. I never had any issues with it. So I don't have any negatives to say about it. But exact is, again, when we have a violation of our assumptions in a 2x2. And that's something, again, you'll know before you actually get to this point. For our statistics, we're going to run chi-square. We're going to run a contingency coefficient, phi and Kramer's V, and then lambda. I've always used these. This is what I've been told like from the start. So I've always used them. I've never really noticed a difference in the data when they're not selected. If anybody has and they can err on that, that'd be helpful. But other than that, I haven't really noticed a huge difference when using those. And then finally, when we're looking at our cells, we want our observed, again, what we actually found, and then the expected, which is, again, what the chi-square model is expecting based on the null hypothesis. I also like doing percentages down here just to see what percent of the sample falls into each of the categories. It makes it easier to interpret as opposed to using raw numbers, just because if you have differences in group sizes, those raw numbers might lead you on the wrong path, whereas percentages might give you a better idea of the data. And then our residuals. I always select standardized or adjusted standardized. They've given me the same results using both. Unstandardized, I've not used. I don't know necessarily what differences it might present. So just stick with standardized and adjusted standardized if you're going to use chi-square, unless you have a reason to use unstandardized. So we run our output. This is what we see on the bottom. What you're going to see when you first get your output, you're going to get your mean standard deviation. You're then going to get your contingency table. Then you're going to get your chi-square statistic at the bottom. Since we did not violate any assumptions, we're going to use this first number here. What we can see is our chi-square value, our degrees of freedom, and then our significance. Again, this is not telling us that there's a differences between these groups. They're just saying there is an association. So how I would report that is saying that the type of training did have a significant association on whether or not cats danced or not. And we'll get to where the differences are on the next couple slides. If we were going to use Fisher's exact, you can see it here. You do not get a value, but you do get a significance level, which you report. This is our likelihood ratio. Again, this is when you have violation of assumptions and larger than 2x2 contingency tables, so 2x3, 2x4. You can notice that's pretty similar in values, but just make sure you're reporting the most accurate one based on the test that you tried to set up and run. This is the contingency table that you'll see with your output. Again, this will become above your chi-square value. And what we can see here on the left, this is the type of training they receive. So food as a reward, affection as a reward. On the top, did they dance, yes or no? And this is our standardized residuals right here in the green. The yellow is food as a reward and the blue being affection as a reward. So just as a real quick bird's eye glance, what I can see is this number is higher than 1.96 on the negative side. So what that's telling me is that there was significantly lower than expected that did not dance when they had food as reward. What the model is expecting is 23.6. So you can see that 10 is significantly lower based on that model. On the other end, though, we can see that we have a significant result for using food as reward, and they did dance. Our value is 3.6. This is actually a p-value of 0.01. And as we can see here, the number we actually observed is significantly more than the expected here at 14.4. For the percentages, again, this gives you a clear picture of where the sample lays. So when we're looking at this first one, it's left to right. So out of food as reward, 26% no did not dance, whereas 74% yes did dance. The bottom number is more looking at this value compared to your other group, this value. So looking at did they dance? No, 1.1% did not dance with food reward, whereas 91.9% did not dance with affection as reward. Again, we can kind of speculate where those significance are coming from based on the contingency table we looked at before. On the other end, same thing, this 36%. Yes, they did dance with reward. Where the other side, we have 63%. Yes, they did dance with reward. Use caution when interpreting these, though. Just because this value is smaller than this value, it does not necessarily mean affection as a reward was the better group. Again, we have to go back to our standardized residuals. We can see significance here, but we do not see significance here. And on top of that, this residual is negative, meaning even though we had a higher percent of the sample dance as perfection as reward, it really was significantly lower than what was expected based on the model. So when you're interpreting, just use caution and make sure you're looking at the standardized residuals first before you're looking at these percentages, because they could mislead you if you're not looking at the right thing. So based on that data, we can then calculate our odds ratio, which again is our effect size.
Hey, Dave, can I ask a question real quick?
Yeah.
About the expected model on
Yeah.
that last slide. The expected count, I was expecting that to be just like a coin flip.
Yep.
It doesn't look like it's a coin flip though, right?
Yep. It's not. It's based on this equation that I showed y'all earlier. Right there.
Okay, so it's taken into account the different sizes of populations.
Yep. Yeah, it takes into account that, and it's not necessarily comparing each other. It's comparing itself to the model, if that makes sense.
Okay. And then from the count to the expected count, that's okay. Then that's where the associations come from, is how far off from your expected count are you? Okay. Okay.
Basically, yeah, yep, exactly. And again, so kind of backing up and looking at full picture. So again, this chi-square, just this statistic tells me that there is something going on with the data, that the type of training did affect if cats danced or not. But I don't know exactly where that is. When I start to look at this table, I can then delineate, okay, I can see that food seemed to have a more significant impact on if they danced or not, as opposed to affection. Again, that's kind of our post hoc analysis. From there, we can then do our question.
No, I was just saying thanks.
Yep, no problem. From there, we can then determine our odds ratio. Again, this is kind of your effect size when you do your chi-square. And again, this is where it gets kind of confusing because you have to do your hand calculations in math, which I know all of us love. But going back, it takes a while to kind of flip. So what we're trying to see is if they danced or not, yes or no. And did that change based on the kind of reward, the other kind of training that they had? So we can see here, we had 28 yes, 10 no. If we go to our next slide, dancing after food, we have again 28 over 10, so we get a number of 2.8. That's going to become our numerator. So that's that A over C that we saw earlier in the slideshow. We're on the other end, we're then taking the number that did not dance. If we look back here, we have 48 over 114, which gives us a value of 0.421. We then plug that into our model and we get an odds ratio of 6.65. So what that is telling us is that cats were 6.65 times more likely to dance when they had food as a reward as opposed to affection. So again, going back to yes, there is a difference, but I'm not necessarily saying that there was a significant difference between the groups. I'm saying that they're more likely to dance after food as opposed to affection, which is this the write-up you could probably use in a manuscript. So there was a significant association between the type of training and whether or not cats would dance, with our chi-square value of 25.36 and our P of 0.001. Based on the odds ratio, the odds of cats dancing were 6.65 times higher if they were trained with food than if they were trained with affection. And that's pretty much all you have to do for your interpretation. You're all done. You already have your effect size. Power, I've never really reported with chi-square. So I don't know the rules on that or if they need to be included. But I've always been told that if your assumptions are met, your power is fine and you're good to continue and move on and interpret the way you normally. So that's it for chi-square. And that was a real simple 2x2 table, but there might be situations where you'll have larger than that. You might have a 3x3 or a 4x4 or a 2x2x2. If that is the case, you're going to use log linear analysis. Now, log linear is a little bit different in the test that it runs, but at the end of it, what it basically does is run the chi-square again. and you get kind of the same results that you did before. So using our same example that we use with the dogs and with the cats, we're going to add now dogs to it. So now we have a 2 by 2 by 2 contingency table. And what we're looking at, if dogs or cats are more likely to dance if they have food or affection as a reward. Down here is the different outcomes we can see, we could possibly have. So we have animal, we have training, we have dance, we have animal by training, animal by dance, dance by training, animal by training by dance. What the linear or what the log linear analysis is going to do is put each of those into the model and see which one contributes most or is most significantly contributing to the model. Then based on that, we can go ahead and interpret our results after that. And you'll see that in a second here. So what the model does is use backwards simulation, similar to when we use logistic regression and other regressions. What it's basically doing is plugging everything into the model and then eliminating one by one, like I just said, to see which is the most significant to the model. If the new model is no worse than the old one, so it starts with the highest, so it would be this one right here, the animal by training by dance. If there is no difference between this and the old model, it'll then throw dance into training in, and then it'll throw animal dance, animal training, et cetera, until we find the most significant contributor to the statistic that we find. So log linear and SPSS, if you go to analysis, log linear, and then you go to model selection, log linear analysis, you can then enter your variables. Your range are going to be 0 to 1 because everything we have is either a 0 or 1, yes or no, or cat or dog. So there is no other range that we have to include. When we do our options, we're going to include frequencies, our residuals as we did before, our parameter estimates, and our association table. Once you do all that, you can go ahead and continue, and it will print out. And you're going to notice you're going to get a ton of more tables than you with the chi-square, a lot of information. Only bits and parts of it are actually important to us. So I'll point out which exactly. So first, you're going to get your cases, how many are in each. You're then going to get your cells counts and residuals. However, just know that with this table first, it adds 0.5 to all of your counts. So you'll notice here that they're all a little bit off. So when reporting results, I wouldn't use this table. I'd use the next one I'm about to show you in a second here. But this just shows you your cal counts and residuals. It then does the goodness of fit test. And what this is basically telling us is how well does our model predict what the outcome would be if this was in another sample of individuals. We can see that our model is significant, meaning that it's a poor fit. So most likely what this means is that if we did the same experiment in a different group of individuals, we might not get the same statistic. Still need to report it, but you can still move ahead with the analysis and get your final results in a second here. So up here is that backwards elimination that I was talking about. So what is it doing? It's adding all factors into the model and then removing each factor to see if there's an effect or not. And what we can see is there an effect on every single one of the factors. So the 3-way, the 2-way, the 1-way, there is significant effects. And down here, the parameter estimates tells us which one is contributing the most to the model. We can see here that the most that are contributing are the animal training and dance, the animal training, as well as the animal and training, where dance and animal and dance are significant, but not as low as the other ones. This is again just telling us what is going to be used in our final model. So all of this stuff is important, but it's more of just information for you to understand what your data is looking like. But what we're really concerned is these individual statistics. So our first is our step summary. Again, since we saw that on the last slide, the animal by training by dance was most significant, that's what was thrown in the model. And what it does is then it removes each one of these interactions one by one until we have a significant effect. However, we do have a significant effect with all 3, so none were removed. So this is our chi-square that we come up with is 20.305 with a significance of 0. Again, this is telling us that there is a significant association between animal, training, and dance. If one of these were eliminated, so for example, animal, and we had a significant association between training and dance, we would just know that there's association between those 2 variables, and animal did not affect the data at the end of the day. This here, again, is giving us our cell counts and residuals, but you notice that 0.5 is gone. So these are the more accurate outcomes that we can see and report in our write-up. So once that first model is determined, it then will take a chi-square of our two variables that we're trying to find the difference of, or the associations of. So you can see we have two different chi-square tests here, one for cats, one for dogs. The cats is the same one we ran before, so nothing has changed, where the dogs is a little bit different, and it's obviously new data. We do have a significant chi-square at 0.04. If you round it up, you might be on the bridge, but we can see that both had a significant effect on the type of training and whether they danced or not. However, again, we don't really know where that significant association is quite yet. This is just another visual interpretation of the data so you can see what it looks like. You can select this option in SPSS, but it's just there to see visually what it looked like. And again, what we're seeing is it looks like, yes, for cat, we see a decent percentage that did dance when they had food as opposed to when they did not. So coming back to our odds ratio, we've already did it for cats in the data before, so it's the same thing, but for dogs, we're going to do it for now. First, for the odds of dancing after food, we had 20/14, which gives us 1.43. Odds of dancing after affection, we have 29/7, which is 4.14. We then take the odds of that, and we see that dogs only have a 0.35 odds ratio, meaning that they are only 0.35 times more likely to dance after food as opposed to affection. Now, what does that exactly mean for our total analysis of everything we were looking at? So when we report it, what we're going to look at is that first log linear right here, this value right here. So what that tells us, again, that there is a significant association with the animal training and dance at 20.31 with a p-value of less than 0.001. We then look at our follow-up chi-square test that we did, we saw on that last slide. What we found is for cats, there was a significant association between the type of training and whether or not they were dance at 25.36 and less than 0.001. And this was also true for dogs that we saw in that previous p-value at 3.39 or 93 and 0.047 p-value. However, the odds of dancing were 6.65 times higher after food than affection in cats, but only 0.35 in dogs. Or another way to interpret is that the odds of dancing were 2.7 times lower if trained with food compared to affection. So what our overall result is that we found is the analysis reveals that cats are more likely to dance for food rather than affection, whereas that's the opposite for dogs. That's log linear. Again, there's a lot more steps and a lot more information to interpret, but at the end of the day, what you're basically doing is a chi-square, and it's the same way you would run it before, and it's the same odds ratio you would determine after that. The final one I'm going to go into, which I don't have a ton of experience in, but I will just touch upon, is the—
Can I ask another question, Dave?
Yeah.
On that last one, on the odds ratios, how you present them. So you've done it in the same sort of order for cats and dogs, food, then affection.
Yep.
Is there any problem of doing it the other way, of saying, 6.5 times or higher odds food than affection for cats, but then 3 times affection than food for dogs?
Yeah,
or is it
No,
proper to only do it in that same order because that's how you did the math?
No, you could report it, but just know that they'd be 6.65 times lower or less likely to dance after affection than opposed to food. So you just have to switch basically what you're interpreting. But it really comes down to what your questions are and how you present the data. Are you really trying to find if food was more effective or if affection was more effective? So yeah, it comes down to really how you set up the question and how you set up the analysis. But either or does work for interpretation.
If the question was, how do I get my animals to dance?
Yeah.
Food or affection, would that have affected how you set the equations up in the beginning?
No, it wouldn't have. It'd be the same thing because we're still trying to figure out if food or affection are more effective. And this still tells us that food is more likely to result in dancing as opposed to affection.
Okay. Well, and the reason why I ask is like the way this reads to me is that if you want your dog to dance, if you give them food, you're less likely to have that happen.
Correct.
They did dance with food. They just danced less than the cats danced.
Yes. And it's again, if you're trying to see if they dance, period, then yes, it is significant for us to find that they're 3.35 times more likely to dance with food. But the other end, we also could report that they're 2.7 times more likely to dance with affection as opposed to food. It's just, again, all what you're trying to, what your general conclusion is going to be. If you're trying to find, do they dance in general, or do they dance more likely with one or two of your outcomes?
And then you just also, I was making the mistake of, it's not 0.35 times, it's 0.35 odds. So I was thinking 0.35 was less than 1, but it's 0.35 greater than 1.
Yes.
Right? Okay.
Yes. So they're still
odd.
more
It's
likely to dance with food, but slightly if you did nothing, basically.
Right. Thank you.
Yep. So the final test I'm going to go over today is McNamara's test. I've never personally used this, but I have seen it done and I have read it in papers. And I just wanted to show you the slide because it's a little confusing to get to the McNamara's test. So what you're going to do is, and this one's looking at non-smokers and smokers before and after an intervention. So it's a little bit different data, but it's trying to find the same outcomes as far as association. Is there a difference between, or is there association between the type of intervention they received and if they were smokers before and after? So how you're going to find McNamara's test is if you go to analyze, then non-parametric, and then legacy dialogues, and then finally 2 related samples, which is going to give you a window like this. Similar to paired t-test and other repeated measures, you're going to pull your variables you're trying to compare over to here, and then you want to make sure you select McNamara test. The output, luckily for this, is a little bit easier to comprehend. You're basically going to get 2 boxes. You're going to get your N for each, so before and after smokers and non-smokers, and then simply our significance. And that's all you're going to get, and that's what you're going to report for your McNamara's test. So it's a little bit easier to report, but a little bit more difficult to set up in the long run. But again, this is when you're using repeated measures. And if you're doing more than that, you're going to use Cochrane's Q test. I think that's what it's called. But we're not going to go over that today. So important things to kind of remember as you're doing your chi-square. Again, independence, each cell must be their own data point. It shouldn't be crossed over between multiple data points. When the expected frequencies should be greater than 5 for each cell. And you'll notice here, which I failed to point out, in your chi-square down here, it'll tell you the percentage of cells that violate that assumption. So it's not something you necessarily have to calculate or look for. It'll tell you right then and there what the issue is. And if you have multiple groups, then it'll tell you which groups specifically are violating that assumption. One thing you can do or kind of account for this assumption is if you have a very large consistency table. So when I was running my dissertation, I had, I think, 4,000 participants. So even though I violated the assumption in some instances, I had less than 20% of the expected frequencies below 5. So even though it was violated, I still reported it, but still let the reader know that this assumption was violated and to interpret with caution. But even though it was still less than 20, so it was still okay to move forward. However, one thing to pay attention to is in these larger contingency tables, you should have no expected frequencies below 1. This is where you have a lot more problems and a lot bigger loss in power. Again, if you do have that issue, my recommendation is to dichotomize or combine some of your variables to hopefully reduce that issue. For me, what I did is I was looking at obesity in kids, and I was looking if they were categorized as underweight, healthy, overweight, or obese. What I found was there was not that many individuals in my sample that were underweight, and adding that 4th category really threw off my data. So what I just simply did was combine them as either healthy or underweight, and only had 3 groups as opposed to 4, which made those assumptions be less likely to be violated for me. Going back to our looking at our cells and our percentages, proportionally small differences in cell frequencies can result in statistically significant associations between samples between variables if sample is large enough. This goes back to basic understanding of stats, where the larger sample size you have, the more likely you're going to get significance, where the lower sample size you have, the better effect size you may get. So just know that's a caveat with this test as well as other tests. That's why it's important to look at the standard residuals, just because that chi-square statistic might not tell the whole story, where the standard residuals can tell you exactly where you might be seeing these differences. This is just kind of a visual understanding of the process of a chi-square, just to give you another look at it. Again, we're checking our expected frequencies. If we have one predictor, all we're going to do is run a chi-square. We're going to look at our standard residuals and then our odds ratio. If we have more than one predictor, we're going to do our log linear analysis, which by the end of our log linear, we run our chi-square as usual, looking at our standard residuals and then our odds ratio. So to sum up, in general, chi-squares are very much similar to other analysis we run, but we're just running with categorical variables, and what we'll report changed a little bit, as far as we're not necessarily reporting means, because the means doesn't really tell us anything, but we are reporting frequencies, we are reporting the fit of the model, we are reporting percentages in each of our cells in our contingency table. When we have two categorical variables, so a 2x2, you're good to run a Pearson's chi-square as well as a likelihood ratio. Again, if you violate assumptions in a larger than 2x2, so a 2x3, a 2x4, that's when you'll run the likelihood ratio test as opposed to Pearson's. When you have 3 or more categorical variables, that's when you're going to run your log linear. But if you have 2 paired, you're going to run your McNamara's test. And that's pretty much all I got. And I can open up for questions now.
Will you give an example of where the association difference thing matters in the dog and cat dancing? So we showed there's an association between dogs dancing and food and affection. We show there's association between cats dancing and food and affection. And we did show there's a difference between cats and dogs and food and affection, didn't we?
Yes, we did. Yeah, I'm more saying that when you find that chi-square statistic, that's not telling you necessarily that there's a difference between groups. It's just telling you that there's an association between your first category variable and your second category variable. When we run our odds ratio and our standard residual, that's where we can see that there is a difference. So in conclusion, based on that dogs and cats example, I would say, yes, dogs and cats are different. Cats are more likely to respond to food as reward as opposed to dogs. It's just in that initial chi-square that just because you see significance doesn't mean, okay, my groups are different. It's just telling you that there is an association between your 2 variables. Does that make sense?
And the groups are different. Are you saying the cat food and cat affection group are different?
Going back to our cat affection group, when we compare just cats, the differences are between food and affection, where food is going to result in more dancing than affection. But when we look at our cats and dogs group, we do see that both food and affection, or food increases both, but we see that food increases cats at a higher rate than they do dogs. So I would say that there are differences between those 2 groups, cats and dogs, where food has a much more likely chance of resulting in a dance as opposed to dogs.
But the chi-square variable itself doesn't necessarily show you that, because there could be different associations between cats and food and cats and affection, dogs and food, dogs and affection.
Correct. So if I look at back at this chi-square statistic right here for our log linear. So yes, this is significant, but I don't know how it's significant. I don't know if food was better, affection was better. This chi-square is not comparing cats and dogs. We compare those using the odds ratio. So that's where we saw here that cats were 6.65 times more likely to dance than dogs. So that's why we can finally conclude that food seem to have a bigger effect on cats than it does dogs when they come to dance.
So the warning is, you see a 25 and a 6, or whatever the chi-squares were, 25 and 3.
Yep.
Yeah, you see those two and they're very different numbers, but you don't really know how different or if they are different because those are associations within those groups.
Correct.
Okay.
This is associating cats with our dancing and our food and affection variables. Same thing here for dogs.
And that's then where you did the animal training effect, looking for all those three, because it does matter if it's a dog or a cat. Okay.
Yes. And if it didn't matter if it was a dog or a cat, that's where in that model, it would then throw animal out and it would just look at training and dance.
Gotcha.
But we did see based on this statistic and this statistic that the type of animal did, and we can see that with our final results where they were way more likely to dance with food as a cat as opposed to dog.
Okay. Great. Thanks.
You're welcome.